Hi, welcome to the LISA webinar on inherent battery chemistry. I'm Dicken, the project manager of LISA project from Leitat. LISA stands for lithium sulphur for safe road electrification, and we're here to talk about this different battery chemistry compared to what's conventional at the moment. So what is the LISA project? So it's a research innovation action, meaning it's quite innovative and with quite a low TRL. The total budget is just below 8 million euros, and we're made up of 13 partners from 7 countries, being research organizations, SMEs, large manufacturers across the whole battery value chain. We're now entering the final year of the project, so it's exciting times. What are the objectives? So at its core, LISA is about having a better battery technology with safety at its core. Our objectives are quite bold. The first being that we develop a safe technology, even when we go beyond standard operating conditions. This is abusive testing, ensuring that there's no thermal runaway, no fires or explosive risk, or toxic gases released. We're trying to develop a denser cathode. We're trying to reduce weight by 30% and the thickness of unit cell stack layers by 48%. And in terms of technical specs, we intend to deliver lithium sulfur pouch cells at a 10 amp hour size that costs below 70 euros per kilowatt hour, with 450 watt hours per kilogram, 700 watt hours per litre, and capable of over 1,000 cycles. What's also important for LISA is that we have at least 50% recyclability. Our fifth objective is that we'll be developing state-of-the-art state of charge and aging estimators for a battery management system, and we're going to assess the second life uses. We'll be validating PLD processes for solid-state electrolytes and validating coating processes also. We'll also be conducting environmental economic assessments with LCA and LCC, and we'll be assessing its integration for battery electric vehicles and e-buses. Now, the LISA project is the spiritual successor of the Elise project, which managed to achieve 310 watt hours per kilogram with a 240 watt hours per litre and for 50 cycles. We're trying to make a substantial improvement to this with 1.5 times more watt hours per kilogram, 3 times greater volumetric energy density, and 10 times the amount of cycles. So what is lithium sulfur? So lithium ion and lithium sulfur batteries use an intercalcation mechanism where basically the lithium ions are shuttled between electrodes where they're stored. Lithium sulfur differs because it uses a conversion mechanism where we take elemental sulfur and lithium and they react to form a series of lithium-containing sulfur compounds, which we call polysulfides, and these deliver the energy stored in the cell. Now, this polysulfide also has the negative, which is something called the polysulfide shuttle effect. This is where there's a dissolution of polysulfides in organic liquid-based electrolytes, which can lead to severe corrosion at the anode and poor cycling stability traditionally. Now, LISA is trying to get beyond these technical barriers to try and unlock the potential of lithium sulfur. Graphically, this is a voltage charge-discharge curve for lithium sulfur batteries, for a very typical one, and it shows the intermediate species that are formed via this conversion mechanism. Now, typically, when the battery is discharging, we end up with a lot more Li2S2 rather than going all the way down to Li2S. So just to try and compare and contrast, obviously lithium sulfur is an old technology, but not as mature as lithium ion. There's a lot of backing towards lithium ion at the moment, and of course there will be in the future. And what we can see here is that we're comparing 6 different categories in a kind of a very broad sense. But we anticipate that the future of lithium sulfur is quite bright, and we believe that gravimetrically, even now lithium sulfur competes with lithium ion, but we'll go even further beyond that, particularly due to its high theoretical limit of 2,500 watt hours per kilogram. Another benefit of lithium sulfur is that it's cobalt-free with little to no critical raw material usage. It's quite lightweight, very cheap compared to current materials. It's also stable at low depths of discharge, unlike current lithium ion, which requires quite complex battery management systems and protection circuitry. It also offers us a diversification of battery technology, ensuring that all our eggs aren't in one basket. But there are a few drawbacks, of course, because why haven't you got lithium sulfur in your phone? So we have a poor cycle life that's caused by this polysulfide shuttle effect, and also it has a much more complex working mechanism, which is more difficult and challenging to understand. So there's definitely a technical barrier in terms of actually getting to grips with the technology. This poor volumetric density as well, which is not in here, but it can be seen as a challenge, particularly for vehicle applications where space is limited. Now, I won't be digging into the entire technical concept of LiSA today, but LiSA's much more refined than her predecessor. Our application of solid-state electrolytes, catholytes, and polysulfide shuttle barriers really help fight against this PS shuffle, increasing the cycling stability and leading to a lot more practical battery. The rise of solid-state electrolytes now is very interesting for us, particularly because it helps mitigate this PS shuffle, which can really unlock the unrealized potential of lithium sulfur. As a research innovation action project, we start from quite a low TRL of 3, and we'll end up at TRL 5. So we're starting where materials are validated and developed and improved at lab scale. And as of today, we're at the stage where our pilot lines are gearing up for production, and will ultimately produce 50 to 100 cells as prototype runs, which will then be validated for state of charge, safety, and recycling assessment. One big hooray of the project is that we achieved a key milestone, which was reaching 400 watt-hours per kilogram demonstrated at an 18 ampere cell level, so a pretty decent sized cell, which we're very pleased with. So just share with everyone. So to go into the safety challenges of battery electric vehicles. So unfortunately, there's a bit of a public perception that lithium-ion battery electric vehicles present a fire risk. This is normally due to the high-energy batteries having a risk of thermal runaway, which can lead to these fire events. Now, only 0.006% of battery electric vehicles have actually caught fire, and that's comparing it to 0.07% of conventional vehicles, which you ask, why have got this bad reputation? But the unfortunate truth is that conventional fire in a vehicle would need only, I say only, it's still a lot, but 2 to 4 tons of water to put out. Compare that to 115 to 150 tons of water for a battery electric vehicle. Now, I have nothing against Tesla. These are just news reports, pictures. So when we consider the entire safety model as a whole, if you look at the right-hand side of the screen, you can see that there's a number of layers to this. So working outwards in, we have the more societal external factors. These are emergency services, ultimately the last line of defense for helping people. Then we have the environment and the infrastructure. So is there any way that our surroundings can mitigate these fires when they do occur? Then we have vehicle, then the battery system, the cell, and then finally the chemistry. So we can mitigate the risks through inherently safe design that can prevent thermal runaway. These can be designed to reduce the propagation of heat and stop one cell from leading to multiple cells failing. We can also have better battery chemistry. This could be through lithium sulfur, or we could avoid any flammable electrolytes within current lithium-ion models. So when we're focusing on these, so LiSA project really focuses on these inner 2 levels where we can eliminate safety risk at the source. So the steps to avoid this are preempting the thermal runaway altogether, detection. So when that does occur, we can have a warning. Then intervention, so stopping it from occurring. Then containment, so it has happened and we're minimizing the damage. Now here's a quick video just showing lithium sulfur being pierced compared to a lithium ion being pierced. Hopefully the video isn't too loud. But in summary, you can see that the lithium ion battery has created a lot of dark smoke. It's been a deformation as well. And the temperature has increased greatly. I believe it's around 300 degrees. Versus the lithium sulfur, which continues to operate, albeit at a slightly raised temperature and a slightly decreased voltage. So what we're doing within the project in terms of testing is UN 38.3 transport validation testing. So this is United Nations standard that lithium-based batteries must need for certification for safe transport. So these 8 tests are altitude simulation, thermal test, vibration testing, shock testing, external short circuit testing, impact crush testing, overcharge and forced discharge. But what I'm more interested in at the moment is EU car hazard level testing. So EU car is the European Council for Automotive R&D, and they established this set of safety standards where level 4 or lower is expected as a minimum possible for integration in electric vehicles. Now, as you can see here on the table on the right, that level 4 is still quite a serious incident should something go wrong. No explosions, but the release of gases, venting, and fire and combustion. And with LiSA project, we're aiming to be as close to level 0 as is practicable, and we'll be conducting tests on multiple cells, both at the beginning of their life and also at the end of their life, to try and qualify them. So the tests involved here, there's 4 separate tests. So there's a nail penetration, an overcharge test, short circuit testing, and thermal abuse testing. So the nail penetration is very simple. A fully charged cell penetrate through its center, and then we see what happens. The overcharge testing involves a fully charged cell once again, where it's further charged with a C over 2.5 current until a destructive event takes place or 24 hours has gone. The short circuit test involves the battery being short circuited and held for at least an hour. And then the thermal abuse test involves trying to determine the temperature where the cell becomes unstable, and trying to quantify the amount of thermal energy that's released by the cell. Also, any gases that are generated within this will be collected and analysed. So just in a nutshell, so lithium sulphur safety. So we're really anticipating that the batteries developed within LiSA project will pass all of these safety testing. The safety has been built in. It's inherently safer through chemistry. And as solid state electrolytes become better understood and more widely available, we believe that the technical barrier of that PS shuttle and that associated short lifespan will be mitigated. And LiSA project's scheduled to be fully completed by December 2022. So keep watching. We'll be releasing more information as we enter this very interesting time for the project. So key takeaway of LiSA is that there's a number of advantages provided by lithium sulfur: high theoretical gravimetric density, cheap prices, low environmental impact, and it allows us this diversification of battery technologies. So thank you for the time. And if you want to find out more information, join us at lisaproject.eu. Follow us on Twitter at H2020Lisa. And my contact details are acdicken@leitat.org, where I'll be happy to answer any questions. Thank you very much for listening, and have a nice day.